Space, the ultimate frontier of human exploration and scientific discovery. For centuries, we've gazed at the stars, asking questions about our place in the universe. Today, advanced technology and groundbreaking research are finally providing answers, but with each discovery come new, deeper mysteries. Join us as we delve into some of the biggest and most terrifying mysteries in the universe. The mysterious hexagonal storm at Saturn's North Pole has fascinated scientists since it was first discovered by the Voyager spacecraft in the 1980s. This intriguing weather phenomenon spans approximately 20,000 miles, dwarfing many of Earth's largest storms. Initially, its geometric precision seemed almost too perfect to be natural, prompting a series of theoretical investigations and lofty speculations. After years of study, researchers now believe that the hexagon is formed by atmospheric phenomena specific to Saturn's unique conditions. The jet streams in Saturn's atmosphere circulate with such incredible speed and over such vast distances that they create standing wave patterns. These waves form tight geometric shapes rather than the more amorphous storm formations seen on Earth. One key factor in the hexagon's formation is a phenomenon known as Rossby waves. On Earth, these waves influence large-scale weather patterns and ocean currents, but on Saturn, their behavior is magnified. Saturn's gaseous composition and lower density allow these waves to interact across greater distances with less friction. Essentially, the jet stream at Saturn's North Pole rotates at about 200 miles per hour, leading to the development of stabilizing forces that structure the gases into a hexagon. Additionally, temperature variations play a role. The interior of the hexagon is warmer compared to its periphery, causing shifts in atmospheric pressure that help maintain its rigid boundaries. Thus, combining high-speed jet streams, fascinating planetary wave interactions, and temperature gradients results in the stunning hexagonal storm that continuously mesmerizes scientists and stargazers alike. Venus is an enigmatic neighbor in our solar system, not least because of its peculiar rotation. Unlike most planets which spin from west to east, Venus rotates from east to west, completing one turn every 243 Earth days. This retrograde rotation, as it is called, intrigues scientists who seek to understand its origins. The leading hypothesis suggests that Venus may have experienced several significant, colossal impacts during its early formation period. These cataclysmic collisions could have supplied sufficient force to alter the planet's rotational direction and speed drastically. Given the chaotic early solar system, where violent impacts were frequent, this explanation holds considerable weight. Moreover, tidal interactions with the Sun further complicate this slow, backward spin. Venus's incredibly thick atmosphere, which is primarily composed of carbon dioxide, creates severe atmospheric tides. These tides interact with the planet's surface to generate frictional forces that could gradually affect its rotation. Over billions of years, such interactions may have resulted in the alteration of Venus's spin to its current retrograde state. Additionally, computer models simulating the planet's dynamics also suggest that gravitational interactions with the Sun might have played a cumulative role. Thus, a combination of colossal impacts in its youth and ongoing atmospheric and gravitational interactions appears to have conspired to make Venus the slow-spinning, backward-rotating planet that it is today. Jupiter's upper atmosphere is astonishingly hot, clocking in at temperatures around 900 degrees Fahrenheit, much hotter than anticipated for a planet situated nearly 500 million miles from the Sun. For decades, this perplexing conundrum has puzzled scientists, as conventional wisdom would suggest that such distant solar radiation should produce significantly cooler atmospheric conditions. Recent research, however, offers intriguing insights into the mechanisms behind this unexpected heat. The answer lies primarily in the planet's powerful auroras. Jupiter's magnetic field is exceptionally strong, about 20,000 times more powerful than Earth's. This magnetic field creates intense auroras, similar to the northern and southern lights on Earth, when charged particles from the Sun slam into the planet's atmosphere. These auroras are not just dazzling light shows, they generate significant amounts of heat. High-energy particles precipitate into the atmosphere, transferring their kinetic energy into thermal energy. This process heats the upper layers of the atmosphere to the extreme temperatures observed. Moreover, the rapid rotation of Jupiter, completing a full spin roughly every 10 hours, helps to distribute this heat more effectively around the planet. In addition to auroras, there are other contributing factors. Studies indicate that gravity waves, which are ripples in the atmosphere created by turbulent airflows, might also play a role in distributing heat from the lower layers up to the upper atmosphere. These waves break and dissipate energy high above Jupiter's cloud tops, adding further warmth. Thus, the confluence of dramatic auroral heating and the action of gravity waves working in concert reveal a complex yet captivating explanation behind Jupiter's unexpectedly sizzling upper atmosphere. Uranus, uniquely tilted at an angle of about 98 degrees, presents a rare and puzzling configuration among the planets in our solar system. Unlike the near-vertical rotations of most planets, Uranus essentially rolls on its side as it orbits the Sun. The most compelling hypothesis to explain this unusual axial tilt involves cataclysmic collisions. In its formative years, Uranus likely encountered one or more massive impacts with celestial bodies. These collisions, especially if they occurred at oblique angles, could have imparted sufficient angular momentum to tilt the planet dramatically. The leading theory posits that a protoplanetary object, roughly the size of Earth, collided with Uranus, causing the planet to tip over. The consequences of such a colossal impact would be profound, affecting not only the planet's tilt but also its internal structure and atmospheric dynamics. The collision might have generated enough heat to significantly alter Uranus's core and mantle, thereby influencing its magnetic field, which is off-centered and tilted relative to its rotational axis. This impact hypothesis is further supported by computer simulations and models which replicate the observed tilt and corroborate the plausibility of such an immense event reshaping the planet's orientation. The tilted configuration also leads to some uniquely fascinating seasonal variations on Uranus. Because of its extreme tilt, each pole gets around 42 years of continuous sunlight, followed by 42 years of darkness as the planet completes its 84-year orbit around the Sun. This prolonged exposure and deprivation create complex and often severe atmospheric phenomena. Thus, the dramatic tilt of Uranus, most likely the result of ancient cosmic collisions, gives rise to a planet characterized by its distinctive axial orientation and extraordinary seasonal cycles. The enigmatic spokes observed in Saturn's rings have intrigued scientists ever since the Voyager spacecraft first spotted them in the 1980s. These radial features appear as dark streaks and seem to move and change over time, defying initial expectations of the rings being purely static structures. Recent investigations, especially those conducted by the Cassini spacecraft, have provided valuable insights into the formation and behavior of these curious spokes. It appears that they result from complex interactions between Saturn's magnetic field and the particles in its rings. These particles are predominantly composed of water ice, but they interact with the magnetosphere in intriguing ways. The prevailing theory is that micron-sized icy particles within the rings become electrically charged by ultraviolet sunlight or by frictional interactions among themselves. When these particles are exposed to Saturn's strong magnetic field, they become suspended above the ring's plane. The magnetic field tugs on these charged particles, lifting them out of their typical ring orbits and aligning them along magnetic field lines, thereby creating the spoke-like features. This process is similar to the way iron filings align along the lines of a magnetic field in a classroom experiment, but on a far grander scale. Another interesting aspect of the spokes is their seasonal nature relating to Saturn's orbit around the Sun. The spokes are most prominent during the planet's equinoxes, when the rings are edge-on to the Sun. During these times, the increased solar activity likely enhances the charging of ring particles, making spoke formation more pronounced. As the angle of sunlight changes with Saturn's seasons, the visibility and frequency of these spokes fluctuate. Thus, the transient, ghostly spokes of Saturn's rings arise from a remarkable interplay of solar radiation, ring particle dynamics, and the planet's imposing magnetic field, together generating one of the most strikingly beautiful phenomena in our solar system. Mercury, the smallest planet in our solar system, has an intriguingly large iron core, comprising about 85% of its radius. This oversized core presents a fascinating puzzle to planetary scientists, who have developed several leading hypotheses to explain its unusual structure. Initially, it was believed that Mercury's proximity to the Sun played a crucial role in its formation. High temperatures close to the Sun would have caused lighter, more volatile materials to evaporate or be blasted away by solar winds during the planet's early formation, leaving behind a denser, metal-rich body. However, this evaporation hypothesis alone doesn't fully account for the immense size of Mercury's core. To better understand this disparity, scientists have increasingly considered catastrophic impacts as major influencing factors. One prominent theory suggests that during the chaotic early days of the solar system, Mercury may have experienced one or more gigantic collisions with other protoplanetary objects. Such impact events could have stripped away much of the lighter silicate mantle material, leaving a predominantly iron-rich core behind. Computer simulations have shown that a head-on collision with a body about 1/6 the mass of Mercury could produce a planet with the observed core-to-mantle ratio. Adding to this complexity, recent studies analyzing Mercury's magnetic field provide supporting evidence for these theories. The strength and behavior of Mercury's magnetic field suggest vigorous core dynamics, consistent with a large molten iron core. Thus, the oversized core of Mercury likely results from a combination of factors involving its proximity to the Sun and cataclysmic impacts that reshaped its internal structure. This remarkable planetary anatomy continues to offer deep insights into the early solar system's violent and dynamic processes. Mars' two small, oddly shaped moons, Phobos and Deimos, have sparked considerable debate and fascination among astronomers since their discovery in the 19th century. Unlike Earth's relatively large and spherical moon, Phobos and Deimos are irregular, lumpy, and much smaller, with Phobos measuring about 14 miles in diameter and Deimos roughly 8 miles. Their peculiar shapes and sizes have led scientists to two primary hypotheses regarding their origins. The first hypothesis posits that Phobos and Deimos are captured asteroids from the asteroid belt, located between Mars and Jupiter. These moons bear a striking resemblance to a class of dark, carbon-rich asteroids known as C-type asteroids, which are abundant in that region. According to this theory, gravitational interactions and collisions could have ejected these asteroids from the belt, sending them careening toward Mars. Once in proximity to the red planet, Mars's gravity would have captured them, locking them into orbit. This capture event would account for their irregular shapes and the fact that they do not share the same origin as Mars itself. The second hypothesis suggests that Phobos and Deimos may have formed from debris resulting from a colossal impact on Mars. In this scenario, a massive body, perhaps a comet or a large asteroid, collided with Mars, ejecting a significant amount of debris into space. Over time, this debris could have coalesced to form the two moons. This theory gains some traction from computer simulations that support the feasibility of such an impact event, generating moons with the observed characteristics of Phobos and Deimos. Additionally, this hypothesis aligns with the surface features of the moons, which resemble fragmented rubble pile structures. Recent missions and ongoing observations continue to deepen our understanding of these enigmatic satellites. For instance, Japan's Martian Moons Exploration (MMX) mission, aimed at landing on Phobos, will bring back samples that could shed light on their composition and, by extension, their origins. Whether they are captured asteroids or the remnants of a cataclysmic impact, Phobos and Deimos remain as captivating symbols of Mars's dynamic history and the broader complexities of our solar system. Pluto's iconic heart-shaped region, known as Tombaugh Regio, captured global attention when the New Horizons spacecraft sent back the first detailed images in 2015. Named in honor of Clyde Tombaugh, the astronomer who discovered Pluto in 1930, this region has proven to be more than just a captivating visual. It's a window into the dwarf planet's geological and atmospheric processes. The left lobe of this heart, known as Sputnik Planitia, is a vast icy plain primarily composed of nitrogen, methane, and carbon monoxide ices. This area is believed to be a gigantic impact basin formed by a colossal collision early in Pluto's history. The impact that created this basin likely occurred billions of years ago, and it was sufficiently powerful to carve out a substantial depression on Pluto's surface. Over time, cryovolcanism and the accumulation of these volatile ices have partially filled this basin, leading to the smooth reflective surface we see today. The nitrogen ice within Sputnik Planitia is particularly susceptible to sublimation and deposition, which drives active surface renewal. It is reworked by a process similar to convection currents in Earth's mantle, where the nitrogen ice warms, rises, cools, and then sinks again. This continual movement creates the polygonal patterns observed in the region and evidences a dynamic interior. Adding another layer of complexity, models suggest that Sputnik Planitia may play a role in balancing Pluto's orientation. The basin's location near Pluto's equator suggests its mass could have influenced the planet's spin axis, contributing to its current orientation. Active geological processes, a product of internal heat possibly from radioactive decay, also support the ongoing reshaping of Tombaugh Regio. The captivating heart-shaped feature therefore represents a confluence of impactful ancient events and ongoing dynamic processes, making it one of the most geologically interesting terrains in our solar system. Neptune's largest moon, Triton, presents one of the most intriguing and dynamic surfaces in the solar system, characterized by the presence of active geysers. These geysers, discovered by the Voyager 2 spacecraft in 1989, spew plumes of nitrogen gas mixed with dark, carbon-rich compounds several miles into Triton's thin atmosphere. The driving force behind these geysers lies in the moon's unique combination of cryovolcanism and solar heating. Triton's surface is coated with a layer of volatile ices, predominantly nitrogen due to the extremely cold temperatures, averaging around -391 degrees Fahrenheit. Beneath this icy crust lies a mix of other ices and possibly a subsurface ocean. The geysers are believed to be driven by seasonal heating from the distant sun, despite its minimal intensity at Triton's orbit, approximately 2.7 billion miles from Earth. During Triton's summer, sunlight penetrates this thin nitrogen ice layer, warming the darker material below. This trapped energy causes the sublimation of nitrogen ice directly into gas, increasing the pressure beneath the surface. Once the pressure builds up sufficiently, it finds weak spots or fractures in the ice crust, erupting as geysers and carrying entrained dark particles along with it. This explanation is supported by observations showing that the geysers are primarily located in the sunlit regions of Triton's southern hemisphere, where solar heating is most effective. The plumes can reach heights of up to 5 miles and are carried downwind by Triton's winds, forming dark streaks across the surface. These geysers are not only a captivating spectacle, but also suggest that Triton remains geologically active, driven by complex interactions between its surface and the limited but critical solar energy it receives. Intriguingly, the energy needed for these eruptions indicates that even in the cold recesses of the outer solar system, dynamic processes akin to volcanic activity on Earth, albeit at a much lower temperature, continue to shape the landscape. Triton's geysers provide essential clues regarding the moon's composition and internal structure, indicating the presence of both volatile ices and potentially liquid reservoirs beneath its crust, thus making it a focal point for scientific interest and speculation about extraterrestrial geologic activity. The sun's corona, the outermost layer of its atmosphere, has long puzzled scientists due to its incredibly high temperatures, which soar to about 1 to 3 million degrees Fahrenheit. In stark contrast, the surface of the sun, or the photosphere, is relatively cooler at approximately 10,000 degrees Fahrenheit. This counterintuitive phenomenon, where the outer layer is significantly hotter than the inner layer, is often referred to as the coronal heating problem. Decades of research and observations have shed light on several key mechanisms that together might explain this disparity. One prominent theory involves magnetic reconnection. The sun's magnetic field is highly dynamic and complex, constantly being twisted and tangled by the motion of the solar plasma. When these magnetic field lines twist and snap, they release tremendous amounts of energy, which can heat the surrounding plasma to extremely high temperatures. This magnetic reconnection can create explosive events such as solar flares and contribute to the overall heating of the corona. Essentially, this process acts like a cosmic rubber band being snapped, where the stored magnetic energy is suddenly converted into heat. Another vital mechanism is wave heating, involving two types of waves: acoustic waves and Alphen waves. Alpha waves are generated by the turbulent motions in the Sun's convection zone and travel along magnetic field lines into the corona. These waves are capable of carrying significant energy from the Sun's interior to its outer atmosphere. As the waves propagate, they can dissipate this energy in the form of heat, much like how ocean waves crashing onto a shore release their energy onto the sand. Acoustic waves, which are pressure waves generated by turbulence within the Sun, can also contribute, though their role is thought to be less significant compared to alpha waves. These combined processes, magnetic reconnection and wave heating, present a compelling explanation for the high temperatures of the Sun's corona. Yet the precise details and contributions of each mechanism remain active areas of research. The Sun's dynamic magnetic field and the behavior of plasma within it provide a natural laboratory for studying extreme physics, offering insights that extend far beyond our star to other stellar phenomena in the universe. The quest to find Earth-like planets in the universe has intensified over the past few decades, driven by advancements in space telescopes and observational techniques. As we gather more data, it becomes increasingly clear that Earth-like planets might be more common than we once thought. One pivotal player in this search has been the Kepler Space Telescope, which, during its mission from 2009 to 2018, identified thousands of exoplanets. Based on its findings, it is estimated that there could be as many as 40 billion Earth-sized planets orbiting within the habitable zones of Sun-like and red dwarf stars in the Milky Way galaxy alone. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist, neither too hot nor too cold. This criterion is crucial because liquid water is considered essential for life as we know it. Kepler's observations revealed a surprising abundance of potentially habitable planets, suggesting that our galaxy may be teeming with worlds that could, in theory, support life. These exoplanets vary widely in their characteristics, from rocky terrains similar to Earth's to water worlds and planets with thick atmospheres, each offering unique environments that could foster different forms of life. Furthermore, studies using data from the Transiting Exoplanet Survey satellite, TESS, launched in 2018, and the upcoming James Webb Space Telescope promise to deepen our understanding. TESS aims to survey the nearest and brightest stars, potentially discovering thousands more exoplanets, while James Webb's powerful instrumentation will allow us to analyze the atmospheres of these distant worlds for biosignatures, such as oxygen, methane, and water vapor. These missions collectively enhance our ability to determine how common Earth-like planets are and assess their potential to harbor life. While Earth-like planets once seemed rare, current evidence suggests they could be reasonably common in the galaxy. The ongoing and future missions will continue to refine these estimates and bring us closer to answering whether we are alone in the universe or part of a vast, populated cosmic landscape. Life on a tidally locked planet, where one side perpetually faces the star and the other remains in constant darkness, would present a set of unique and fascinating challenges. These planets, often found orbiting close to their parent stars, exhibit extreme environments wholly different from Earth's dynamic day-night cycle. The perpetual daylight on the star-facing side and eternal night on the opposite side would create drastic temperature contrasts, potentially ranging from scorching heat to frigid cold. Understanding how life could adapt to such conditions requires a leap in imagination, but some intriguing possibilities emerge. First, the narrow band known as the Terminator Line, the twilight zone where night meets day, offers the most likely habitat for life. In this region, the temperatures are more moderate, avoiding the extreme heat of the day side and the intense cold of the night side. Plants and photosynthetic organisms might grow in this band, utilizing the steady indirect light while possibly developing unique adaptations to cope with the low light levels. Water, if present, might also congregate here, existing as liquid due to the relatively stable conditions, thus providing a crucial resource for sustaining life. The day side, with its relentless exposure to starlight, would experience scorching temperatures. Life forms here would need extraordinary adaptations to deal with the intense heat and radiation. They might develop protective features such as thick reflective coatings or burrow underground to avoid the surface conditions. On the night side, life forms could be adapted to near freezing or sub-freezing temperatures, similar to extremophiles found on Earth that thrive in polar regions or deep-sea vents. For instance, organisms might rely on chemosynthesis instead of photosynthesis, extracting energy from chemical reactions in the absence of light. Human habitation on a tidally locked planet would hinge on advanced technology and keen environmental management. Settlements would most likely be built along the habitable Terminator Line, designed to contend with intense winds driven by the temperature disparity between the day and night sides. Sustainable energy sources, perhaps leveraging the contrast between light and dark, and efficient systems for temperature regulation and resource management would be essential. As our understanding of exoplanets grows, these speculative scenarios highlight the resilience and adaptability required for life to thrive under such extraordinary conditions. Hot Jupiters are a fascinating class of exoplanets, characterized by their large sizes comparable to Jupiter and their surprisingly close orbits around their parent stars, often completing a full orbit in just a few days. The formation and migration of these gas giants so near to their stars present intriguing questions and have driven several hypotheses aimed at unraveling this cosmic mystery. One widely accepted theory is the migration hypothesis, which suggests that hot Jupiters form much farther from their parent star, in regions of the protoplanetary disk where temperatures are low enough for ices to condense and coalesce into massive cores. These regions, akin to the location of Jupiter in our solar system, allow the accumulation of significant amounts of gas and dust, ultimately giving birth to giant planets. After their formation, these gas giants experience interactions with the surrounding disk material, leading to angular momentum exchanges that cause them to migrate inward. This process, known as disk-driven migration, can pull the planet closer to the star, upending its initially distant orbit. Another complementary model involves gravitational interactions with other nearby planets or planetary embryos. In a young, dynamically unstable planetary system, massive bodies can scatter each other into different orbits through close encounters. This mechanism, known as planet-planet scattering, can result in a giant planet being flung into a highly eccentric orbit. Over time, tidal forces exerted by the star can circularize this orbit, bringing the hot Jupiter into a stable, tight orbit very close to its star. These interactions can also involve Kozai-Lidov oscillations, where a third body induces periodic oscillations in the inclination and eccentricity of the hot Jupiter's orbit, eventually leading to inward migration. These migration processes explain the presence of hot Jupiters in stark contrast to the traditional model of planetary formation derived from our solar system. Observations of young star systems have shown evidence for both types of migration, enhancing our understanding of these mechanisms. Instruments such as the Kepler Space Telescope and upcoming missions like the James Webb Space Telescope continue to provide valuable data, revealing the diverse pathways through which planets find their places in the cosmos. The study of hot Jupiters not only enriches our knowledge of planet formation and migration, but also challenges and refines existing planetary science models. The universe is home to an array of bizarre and extreme exoplanets, each defying expectations and broadening our understanding of planetary diversity. Among the most extreme are, one of the hottest known exoplanets is Kelt 9b. Located about 670 light-years away, Kelt 9b is a gas giant that orbits its star every 1.5 days. It's exposed to such intense stellar radiation that its dayside temperatures soar to around 7,800 degrees Fahrenheit, hotter than some stars. This extreme heat causes the planet's atmosphere to evaporate, creating a tail of vaporized metals and molecules trailing behind it, much like a comet. At the other end of the temperature spectrum lies Ogle 2005 G 390 Lb. Discovered through gravitational microlensing, this planet is roughly 20,000 light-years away and orbits far from its host star. Its surface temperature hovers around -400 degrees Fahrenheit, making it a frigid, icy world. Such extreme cold suggests a surface covered in frozen hydrogen and methane, possibly hiding a subsurface ocean kept liquid by internal heat. The densest exoplanets also present remarkable extremes. For instance, Kepler 10b, located about 560 light-years away in the constellation Draco, is an ultra-dense rocky planet with a density almost twice that of Earth. Initially, it was believed to be an oversized Mercury, its extreme density hinting at a metallic composition much like the innermost planet of our solar system. Kepler 10b's dayside reaches temperatures of up to 3,600 degrees Fahrenheit, likely resulting in molten rock oceans. These are free-floating planets that don't orbit any star, drifting alone through interstellar space. Without a nearby star to provide heat, such planets can have wildly varying temperatures depending on their internal heat sources. CFB-DSR 2149-0403, for instance, has a temperature of about 400 degrees Fahrenheit, likely heated by its own internal processes. One fascinating exoplanet is WASP-12b, an example of a hot Jupiter undergoing a process of tidal disruption. This tidally locked planet orbits so close to its star that it's being stretched into an egg shape by the star's gravity. With temperatures exceeding 4,000 degrees Fahrenheit, this extreme proximity is also causing its atmosphere to be gradually stripped away, forming a trailing stream of material being absorbed by its host star. These extreme exoplanets challenge our traditional notions of planetary formation and habitability, demonstrating the staggering variety of worlds that exist beyond our solar system. Each discovery opens new chapters in our understanding of the universe and the myriad possibilities for planets beyond our reach. In the expanse of our galaxy, binary star systems, where two stars orbit a common center, are not a rarity. Interestingly, despite the dynamic gravitational interplay between the two stars, planets can and do manage to form within these systems, often challenging our traditional models of planetary formation. In a binary star system, planets form in protoplanetary disks, which are dense concentrations of gas, dust, and other material surrounding one or both stars. The presence of two stars means that the gravitational weave is significantly more complex than in single star systems. This, however, does not inhibit the process. Rather, it introduces an added layer of cosmic ballet. As the particles in the disk collide and coalesce, they gradually build up into planetesimals and eventually protoplanets. Research involving advanced simulation techniques has shown that planets in these systems typically form in one of two primary configurations. In circumbinary systems, a planet orbits both stars in a wide, stable orbit, often beyond the reach of the star's chaotic gravitational forces. Alternatively, in circumstellar systems, a planet may orbit just one of the two stars, much closer, while the second star orbits further out. The dual star influence is a significant factor during the growth stages of these nascent planets, leading to potentially unique orbital characteristics. Recent discoveries, such as those from the Kepler Space Telescope, have confirmed the existence of several such planets, demonstrating that nature's ability to create planets is versatile enough to triumph even amidst the gravitational complexities of binary stars. Studying the atmospheres of exoplanets, those planets orbiting stars outside our solar system, opens a window into understanding not only the composition and dynamics of these distant worlds, but also the broader question of habitability and the potential for life beyond Earth. By analyzing the light that filters through or reflects off an exoplanet's atmosphere, using techniques such as spectroscopy, scientists can detect the presence of various molecules, including water vapor, methane, carbon dioxide, and even oxygen. These molecular signatures provide critical insights into the planet's atmospheric chemistry, weather patterns, and potential geological processes. Moreover, the characteristics of exoplanet atmospheres can reveal much about their origins and evolution. For instance, a predominance of hydrogen and helium might suggest a gas giant similar to Jupiter, while the presence of oxygen and water could point towards a more Earth-like world. Additionally, detecting variations in atmospheric composition over time can shed light on active phenomena such as volcanic activity or seasonal changes. Such studies can also illuminate the interactions between a planet and its host star, especially regarding how stellar radiation impacts atmospheric retention and composition. This wealth of information not only enhances our understanding of the myriad planetary systems spread across the galaxy, but also refines our models of planetary formation and sustainability, guiding our search for truly habitable worlds. Super-Earths and mini-Neptunes, those celestial bodies with masses larger than Earth but smaller than that of Neptune, present fascinating insights into planetary formation and the diversity of planetary systems. The formation of these intermediate-sized planets can generally be retraced to the early stages of a star system's birth in a protoplanetary disk, a dense, rotating disk of gas and dust enveloping a young star. In these disks, dust particles collide and stick together, eventually forming planetesimals, which serve as building blocks for planets. The growth process for super-Earths, which are rocky planets with up to 10 times the mass of Earth, often involves the rapid accumulation of material before the gaseous components of the protoplanetary disk dissipate. The core accretion model suggests that these planets form by the gradual buildup of a solid core, which can gather gas from the disk if it's sufficiently massive. However, they typically aren't large enough to morph into gas giants. Conversely, mini-Neptunes, which are defined by their extended atmospheres of hydrogen and helium over a solid core, likely follow a similar growth trajectory, but manage to capture a more substantial gaseous envelope. These planets may form further out in the cooler regions of the disk, where gas accretion is more efficient, or they might migrate inward after their formation. Recent observational missions, such as those carried out by the Kepler Space Telescope, have identified that these categories of planets are among the most common types in our galaxy. The fact that they do not appear in our own solar system adds a compelling layer to the study of planetary systems, suggesting a vast and varied landscape of planet formation mechanisms. Understanding these processes enhances our grasp of planet formation theories, offering clues on the initial conditions and subsequent evolutionary pathways that can lead to the myriad planetary configurations observed in the universe. The quest for identifying an Earth 2.0, a true twin to our home planet, fascinates astronomers and captures the imagination of the public. Scientists are focusing on locating Earth-sized or slightly larger exoplanets in the habitable zones of their stars, where conditions might be right for liquid water to exist. The habitable zone, often referred to as the Goldilocks zone, represents the region around a star where temperatures are just right, not too hot and not too cold, for maintaining liquid water, a key ingredient for life as we know it. Advancements in telescope technology, such as those seen with the Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, TESS, have exponentially increased the number of known exoplanets. These sophisticated instruments can detect the minute dimming of a star's light as a planet crosses in front of it, known as a transit. Through these discoveries, we've identified several promising candidates that tick many of the boxes for Earth-like features, such as Kepler 186f and Proxima Centauri b, both situated within their respective habitable zones. The next frontier involves the detailed study of these candidate planets, particularly their atmospheres, to determine their true potential for habitability. The James Webb Space Telescope and future missions like the European Space Agency's Ariel spacecraft will allow us to scrutinize atmospheric compositions with unprecedented precision. Detecting gas compositions and potential biosignatures like oxygen, methane, and other organic molecules will be crucial in assessing whether these worlds harbor environments conducive to life. While we haven't found an exact Earth analog yet, the accelerating pace of discoveries and technological advancements suggests that finding Earth 2.0 is no longer a mere fantasy, but an exciting, attainable goal within the near future. Rogue planets, also known as interstellar or free-floating planets, are fascinating celestial objects that wander the galaxy without orbiting any star. Their formation and evolution tell an intriguing story of cosmic dynamics and the volatility of young planetary systems. These planets could originate in several ways. One leading hypothesis is that rogue planets form within the protoplanetary disks surrounding young stars, just as regular planets do. However, turbulent interactions and gravitational influences from neighboring planets or passing stars can eject these nascent worlds from their original orbits, sending them drifting into the interstellar void. Another potential formation pathway suggests that rogue planets might coalesce directly from the collapse of gas and dust clouds, following a process similar to star formation but lacking sufficient mass to ignite nuclear fusion. This direct collapse model implies that rogue planets might share more characteristics with brown dwarfs, which are substellar objects that also form from collapsing gas clouds but never reach the critical mass required to sustain fusion reactions in their cores. Once adrift, rogue planets evolve in isolation, unfree from the radiation and tidal forces of a host star. This independence means their surfaces can be exceedingly cold, potentially harboring frozen atmospheres or oceans if they have any liquid elements. However, internal heating sources, such as radioactive decay or residual heat from their formation, could sustain subsurface oceans beneath icy shells, raising intriguing possibilities about their capacity to harbor life in isolated ecosystems. As our detection technologies improve, including gravitational microlensing techniques and sensitive infrared surveys, we've started to identify more of these elusive wanderers, offering valuable insights into the chaotic processes that shape planetary systems and the potential hidden reservoirs of life in the universe. Standing on the surface of a super-Earth, a planet larger and more massive than Earth but still rocky in nature, would be an extraordinary experience, distinctly different from anything we know. Imagine a world where gravity is appreciably stronger than Earth's, given its greater mass. This increased gravity means that every movement, every step, and every heartbeat requires more effort. Depending on the exact mass and radius of the super-Earth, the gravitational force could be anywhere from slightly stronger to several times greater than what we experience on Earth. This would make you feel significantly heavier, reducing your ability to jump or move quickly and influencing how you structure habitats and conduct daily activities. The atmosphere of a super-Earth might also present unique characteristics. A planet with a more massive core could have retained a thicker atmosphere, possibly rich in gases like hydrogen and helium, affecting air pressure and climate. If the super-Earth has a robust magnetic field, it might shield the surface from harmful cosmic radiation, creating potentially habitable conditions. The thicker atmosphere could lead to more intense weather patterns. Imagine powerful storms and possibly denser cloud formations that affect light and heat distribution. If the planet is within the habitable zone of its star, liquid water might exist, altering the landscape with vast oceans, rivers, and perhaps lush vegetation unlike anything seen on Earth. The geology of a super-Earth would also be fascinating. The increased gravity might result in shorter and stubbier mountain ranges compared to those on Earth, as the weight of rock layers is greater and hence they can't rise as high without collapsing. The surface would likely be marked with diverse terrain, which might include vast plains, deep canyons, and expansive plateaus, shaped by the planet's intense internal heat and tectonic activity. Overall, standing on a super-Earth would provide a constant reminder of its powerful gravitational pull and might offer sights and experiences that redefine our understanding of planetary life. Dark energy is one of the most enigmatic and captivating concepts in modern cosmology. This mysterious force constitutes about 70% of the universe's total energy content and is believed to be the driving force behind the accelerated expansion of the universe. Unlike dark matter, which exerts gravitational pull, dark energy acts in opposition to gravity, pushing regions of space apart. Its exact nature remains one of the greatest scientific mysteries, but it is often associated with the cosmological constant, a term first introduced by Albert Einstein in his equations of general relativity, and later revived to explain observations of the expanding universe. The discovery of dark energy stems from the late 1990s, When astronomers observed distant supernovae and realized that these stellar explosions were dimmer and therefore further away than expected. This unexpected acceleration suggests that instead of slowing down due to gravitational attraction, the universe's expansion rate is accelerating, indicating the presence of a repulsive force. Dark energy affects the large-scale structure of the cosmos, influencing galaxy formation, clusters, and the ultimate fate of the universe. If the influence of dark energy continues to dominate, it could lead to a future scenario known as the Big Freeze, where galaxies drift so far apart that stars deplete their nuclear fuel without forming new stars, eventually leaving a cold, dark, and sparse cosmos. Various theoretical models attempt to describe dark energy, including quintessence, which proposes a dynamic field that changes over time, and modifications of gravity on large scales. Upcoming observations, especially from missions like the Euclid Space Telescope and the Wide Field Infrared Survey Telescope, WF-FIRST, aim to map the distribution of galaxies and test predictions about cosmic acceleration, hopefully bringing us closer to understanding this profound aspect of our universe. These studies not only elucidate the nature of dark energy, but also transform our comprehension of fundamental physics and the ultimate destiny of all cosmic structures. Galaxy clusters are the most massive gravitationally bound structures in the universe, consisting of hundreds to thousands of galaxies, vast amounts of hot gas, and dark matter all held together by gravity. The formation and evolution of these colossal structures provide valuable insights into the large-scale properties of the universe. The story of galaxy clusters begins in the early universe, where initial density fluctuations in the cosmic microwave background, a relic radiation from the Big Bang, seeded regions of higher matter concentration. As the universe expanded and cooled, these density fluctuations grew under the influence of gravity, pulling in surrounding dark matter and gas. Dark matter, being the dominant mass component of the universe, plays a critical role as the scaffolding upon which galaxy clusters form. Over billions of years, smaller structures merged through a process called hierarchical clustering. This means that smaller galaxy groups and protoclusters combine to form larger and more massive clusters, gradually building up to the enormous structures we observe today. Throughout this process, galaxies interacted and sometimes merged, altering their shapes and triggering star formation. The evolution of galaxy clusters is marked by dynamic processes. The intra-cluster medium, comprising hot X-ray emitting gas that can reach temperatures of up to 100 million degrees Kelvin, is a key feature of these clusters. This hot gas results from the kinetic energy of gas particles being transformed into thermal energy as they collapse into the cluster's gravitational potential well. Galaxy clusters also experience interactions and collisions that can lead to phenomena such as gravitational lensing, where the cluster's mass bends light from background galaxies, providing a cosmic magnifying glass effect. Studying these interactions not only helps in mapping the distribution of dark matter, but also in understanding the rate of cluster evolution. Advanced telescopes and surveys, such as those conducted by the Hubble Space Telescope, the Chandra X-ray Observatory, and upcoming instruments like the James Webb Space Telescope, continue to enhance our understanding of galaxy clusters. These observations refine our models of cosmological structure formation and evolution, offering clues about the nature of dark matter and dark energy, thus unraveling deeper mysteries of the cosmos. The filamentary structure of the cosmic web, the vast network of interconnected galaxies, galaxy clusters, and dark matter that stretches across the universe, is a direct result of the gravitational influence exerted by dark matter and the dynamics of cosmic expansion. This intricate cosmic architecture is shaped by the primordial density fluctuations in the early universe, which were initially imprinted on the cosmic microwave background radiation shortly after the Big Bang. In the early stages of the universe, tiny variations in the density of matter led to the formation of regions of higher and lower mass concentrations. Dark matter, which makes up about 85% of the universe's total matter content, began to clump together in response to these density fluctuations. Over time, gravity amplified these perturbations, causing the denser regions to attract more matter and grow even denser. This process created a web-like pattern of high-density regions, connected by elongated filaments of dark matter and ordinary matter, with vast voids in between. As gravity continued to pull matter into these filaments, gas and dust followed the dark matter's lead, resulting in the formation of galaxies and galaxy clusters along these vast strands. The intersections of filaments, known as nodes, became hotbeds for galaxy and cluster formation, where multiple filaments converge, creating regions of extraordinarily high density. These nodes are essentially the cosmic hubs of the universe, connected by the filamentary roads of the cosmic web. Modern astronomical observations and simulations, such as those using the Sloan Digital Sky Survey and the Millennium Simulation, have provided detailed maps of the cosmic web, confirming its filamentary structure and enhancing our understanding of large-scale cosmic evolution. These studies show that the cosmic web's texture is crucial for the formation of galaxies and other cosmic structures, profoundly influencing the dynamics and distribution of matter in the universe. As our observational tools and computational models continue to improve, we will gain even deeper insights into the mechanisms driving this grand cosmic tapestry. Cosmic voids, the vast empty regions between the filamentary structures of the cosmic web, represent some of the most fascinating expanses in the universe. These voids, which can span tens to hundreds of millions of light-years across, form as a natural consequence of the gravitational evolution of matter after the Big Bang. In the early universe, slight density fluctuations resulted in regions of higher and lower matter density. Over billions of years, the gravitational force amplified these initial differences. High-density regions attracted more mass, leading to the formation of galaxies and clusters, while low-density regions were left relatively vacant, evolving into cosmic voids. The process of void formation involves matter being pulled away from these underdense regions toward the denser filaments and clusters. Essentially, the rich get richer and the poor get poorer. These voids are not completely empty, but contain significantly fewer galaxies and less matter compared to the denser parts of the universe. The sparse galaxies within cosmic voids are often isolated and tend to be small, dim, and irregularly shaped, unlike their more abundant counterparts in the dense clusters. Additionally, these voids have lower gas content, and any remaining gas is usually at a much lower temperature compared to the hot, X-ray emitting gas found in galaxy clusters. Interestingly, cosmic voids serve as excellent laboratories for studying various cosmological phenomena. Because they are relatively simple environments with less gravitational complexity, they offer a unique setting for examining dark energy's effects on cosmic expansion. The dynamics of how galaxies move within and around voids also provide valuable insights into the large-scale structure and evolution of the universe. Advanced surveys and simulations, such as those conducted by the Dark Energy Survey and the Illustris simulation, have been instrumental in mapping these voids and understanding their role in the cosmos. As research progresses, cosmic voids will continue to reveal intriguing aspects of how the universe and the mysterious forces driving its evolution operates. The largest structures in the universe are awe-inspiring in their scale and complexity, stretching across hundreds of millions of light-years and composed of countless galaxies, dark matter, and intergalactic gas. These colossal formations include galaxy clusters, superclusters, filaments of the cosmic web, and vast cosmic voids, each contributing to the grand architecture of the cosmos. Among these, the most enormous structures are galaxy superclusters, which are collections of galaxy clusters bound together by gravity to create immense conglomerates. One of the most well-known superclusters is the Laniakea supercluster, which extends over 500 million light-years and contains around 100,000 galaxies, including our own Milky Way. Another colossal structure is the Hercules Corona Borealis Great Wall, which is currently considered the largest known structure in the observable universe. This immense wall of galaxies spans over 10 billion light-years, challenging our understanding of cosmic scale and structure. These superclusters, strung together by vast filaments of dark matter and intergalactic gas, form the nodes and connections of the cosmic web. Filaments themselves are enormous, often stretching over several hundred million light-years, and act as the spine of the cosmic skeleton, guiding the formation and distribution of galaxies. The cosmic web's interconnecting structure is punctuated by enormous voids, vast empty spaces that make up large portions of the universe. These large-scale structures provide crucial insights into the universe's formation and evolution. They help astronomers understand the distribution of dark matter and the influence of dark energy in driving the universe's accelerated expansion. Ongoing and future surveys utilizing advanced telescopes and computational simulations continue to map these vast structures in higher detail, revealing the intricacies of the universe on its grandest scales. The study of these structures not only broadens our knowledge of cosmological principles, but also uncovers the fundamental forces shaping our universe's ultimate destiny. Galactic superclusters, the largest coherent structures in the universe, influence each other primarily through the force of gravity and the large-scale dynamics of cosmic expansion. These colossal assemblies, consisting of multiple galaxy clusters and hundreds of thousands of individual galaxies, are interconnected by filaments of the cosmic web, creating a complex network. While superclusters themselves can be hundreds of millions of light-years apart, their gravitational fields extend far beyond their visible boundaries, subtly pulling on neighboring structures and influencing their motions. The interaction between superclusters happens over incredibly long timescales, often spanning billions of years. The gravitational pull they exert on each other can lead to large-scale flows of galaxies and dark matter, often converging towards the densest regions. This movement is sometimes referred to as peculiar velocity, which is the velocity relative to the overall expansion of the universe. These flows can lead to phenomena like the Great Attractor, a mysterious region of space towards which our Milky Way and thousands of other galaxies are moving, influenced by the gravitational pull of several neighboring superclusters. Additionally, as superclusters move and evolve, they can influence the structure of the cosmic web. The dense regions at the intersections of filaments, where superclusters reside, can become even denser due to gravitational accretion from surrounding voids and filaments. High-energy interactions, such as galaxy mergers and collisions of galaxy clusters within superclusters, also play a role in redistributing mass and energy. These events can trigger star formation, modify galaxy morphology, and generate enormous amounts of hot gas and X-ray emissions, enriching the intergalactic medium with heavy elements. Recent observations and simulations, such as those from the Sloan Digital Sky Survey and the Illustris TNG project, are beginning to unveil the complexities of these interactions. These studies help us understand how large-scale cosmic structures grow and evolve, and how their intricate dance shapes the universe's overall architecture. By mapping the motions and distributions of superclusters and their constituent galaxies, astronomers are piecing together the grand narrative of cosmic evolution, offering deeper insights into the underlying forces governing the universe. The Great Attractor is a gravitational anomaly located in the Laniakea supercluster, a mammoth conglomeration of galaxies, including our own Milky Way. Discovered in the late 20th century, the Great Attractor is intriguing because it exerts a significant gravitational pull on our galaxy and many others, causing them to move towards it at speeds exceeding 600 kilometers per second. This peculiar motion is in addition to the general expansion of the universe, indicating that a substantial mass concentration lies in this region. The exact nature of the Great Attractor is somewhat obscured because it's located in the so-called zone of avoidance, an area of the sky heavily obscured by the Milky Way's plane. However, extensive observations in various wavelengths, including X-rays and radio waves, have helped researchers peer through the galactic dust and identify what lies in this mysterious region. It's now thought that the Great Attractor is a complex assembly of several galaxy clusters, with one of the most prominent being the Norma cluster, also known as Abell 3627. Further, the Great Attractor is part of an even larger structure called the Shapley supercluster, which contains many clusters and superclusters, and represents one of the densest and most massive regions in the nearby universe.